Alright, so learning target there is at the top. You're going to understand what dilations are and how to use similarity transformations. A dilation is a transformation in which a figure is enlarged or reduced with respect to its fixed point. So the point in which we're talking about decides everything else on our graph. A dilation with a center of dilation C and a scale factor K maps every point P in the figure to P prime so that the following things are true. So, following our picture here, this point right here, C, is our center of dilation. The pre-image that we're using is the little one here because it doesn't have the prime notation. So that's the pre-image. And then our image is the one after we do the scaling. So we're at P prime, Q prime, R prime. So that's our image. Okay, so that's the picture there that you can see. We got two cases. It says if P is on the center point C, then the point's not going to move. But if the case is that P is not on the center point P, then the point will move and it's going to lie on the ray from C to its pre-image point. So P is on the same line that CP was. We're just going farther out. All right. So, finding the scale factor. The scale factor K is a positive number such that the distance from C prime to P prime is that's divided of CP. So, that's the difference here. Or you can think of it like this if you want. It's the image length divided by the pre-image length. So whatever way you want to think of it is fine. If you think of it as the prime notation divided by the regular, or image divided by pre-image. And then another way, I guess some people think of it this way. I don't think this way helps, but you could think of it as the copy divided by the original. But to me, that's confusing. But if that works for you, then use that. Copy divided by original. All right, so anytime that K value is bigger than 1, it's getting larger. So it's an enlargement. If K is between 0 and 1, it's a reduction. Why don't we have anything that says less than 0?
Because it's less than 0. Oh yeah, shapes can't be gone. Like it's not gone.
Yeah, there's no zero.
Like it can't go away.
No, zero angles can't be negative.
Yeah, they can.
Distances
That's
can't
very
be.
questionable that you answer for me.
Okay, but we're not talking about distance here. We're talking about what we're multiplying it by.
Oh, you can't get less than what you're less than. What you have is.
The negative just tells you you're going in the other direction.
Oh.
Yeah,
So K is either going to be getting bigger because it's either a negative or a positive number that's bigger than 1. It's the absolute value of K. Or K is between 0 and 1, which means it's a decimal, so it's going to be getting smaller. If you got 0, it's not going to change your image at all. You're saying the points are the exact same as they were before we did anything. So 0 just meant nothing happened. Okay. So in number 1, it says find the scale factor for each dilation. Then tell whether it was a reduction or an enlargement. So we need a fraction for K. K equals what divided by what? So this is how I think of it. I think of it as image length divided by pre-image length.
12 divided by 8.
12 divided by 8, which simplifies to what?
3 over 2.
24.
3 over 2, because we can divide top and bottom by 4. If you'd like to write it as a decimal, you can. You can write that as 1.5. It doesn't really matter. So is it bigger than 1 or between 0 and 1?
Bigger than 1.
So is it an enlargement or a reduction?
Enlargement.
All right. So this was an enlargement.
Literally just look at the shape of the cup.
No, you can't.
It's so obvious.
Well, it's better to learn because you're just gotta learn.
Okay. What about in the next one? So now we're done with safety pins and we're looking at paper clips.
30 over 18.
So K equals.
18 over 30.
Woo! Interesting. I heard 30 over 18 and then I heard 18 over 30.
30 over 18, bro. Like, yo, come on, guys.
What's
30
our.
over 18, bro.
It'd be 30 over 18.
The prime image is the smaller one. So our image number is the 18.
It's a comma, it's an apostrophe.
And the pre-image number is the 30.
It's an apostrophe.
It's an apostrophe.
Yeah, it'd be 30 over 18.
So it's 18 over 30. This is my image length. This is the pre-image length.
Oh!
So make sure you're noting that this was the image in the first one, but this was the image in the second one.
Yo, that literally makes like no sense.
So you just have to read the notation.
But the
It's
other
an
one, that one's
apostrophe,
bigger.
not a 1.
All right. So what is 18 over 30 reduced to?
3 over 5.
So is this an enlargement or a reduction?
We have studied in this field.
A reduction. That number is between 0 and 1. All right. In number 2, it says you're using a magnifying glass that shows the image of an object that is 6 times the object's actual size. Determine the length of the image of the spider seen through the magnifying glass. So if you've ever looked at the mirrors on a car, the 2 side mirrors, the mirror on the right, so the passenger side, says images in the mirror are larger than they appear.
Oh,
Because-
down the bottom.
Yes, they've magnified it so that you can see farther behind you. But the left one is not,
Wait, why not the left one? The left one's the driver one.
because you can see that. It's right next to you.
Wait, what? What?
Because you can just turn and see if there's a car next to you. On the right side, you can't, because you have to look behind you and back.
Passengers to
Wait.
see what was going on, not the driver.
No, it's not.
What?
No feature in the cars for the passenger other than the seatbelt and the airbag. I hate to break it to you.
And the seat.
And the seat.
In the couple.
All right.
Literally from the same.
There's no way.
So in number 2,
That's part of those, like, look out of.
what is our scale factor?
Oh, yeah, that's right.
6.
Okay, so if this is our scale factor, K equals 6. What are we going to do with that? If this was the image that we have of a real spider, because it says determine the image, so this is the pre-image.
Oh, yeah.
So 1.5 centimeters is really like this, right?
What? That's like an inch.
What?
That's like an inch.
Okay, now I'll get a ruler. I probably have
I'll
to
bet
go
you
to
like
the-
$1 million that's an inch.
Have you seen those TikToks where they like hold the tape measure and they're like, show me 18 inches, and it's like backwards and they have to like.
That's literally 0.8
Yeah, I wanna
centimeters.
try that. I can
That's
still do
0.8.
All right, let me see how far off I am.
That's 0.8 centimeters.
Oh, mine's not even long enough in the slightest. Mine's only exactly
I told
one.
you. I told you.
That's a centimeter, Josh, not an inch.
Oh.
So it should have been here, yay.
We're talking like 5.
All right, so 1.5 centimeters.
No, I'm not, bro.
So how do we figure out how big it would be under the magnifying glass?
4, 3, 3, 3. 3, 3, 3.
Multiply by 6.
I'm stunned. Yes, Connor. We
Oh,
are
nine,
multiplying
nine,
our
nine,
pre-image length
Obviously.
by our scale factor, which was
9, 9.
6.
Six.
So 1.5 times 6.
9, 9, 9.
Turn this not Josh.
I think it actually might have been 9.
So it would really be, since we're going to be particular here, this length, which would be 9 centimeters.
Wow.
So the way we got there is we did the 1.5 times 6.
Light work.
How many centimeters are in
Miss Sweeney.
12, 24, or 12.
Like 2.2 or something?
I thought there's 12 centimeters in an inch.
No, there's 12 inches in a foot.
Oh.
All right, moving on.
That's literally like the same thing.
What are the coordinate rules? So if we're on a graph for doing a dilation. So to create a dilation centered at the origin, 0, 0, which is right here where the two lines cross, with a scale factor of k, we take our original point and we multiply each of the pieces of our coordinate by the scale factor. Okay? So, what?
What if you don't know the scale factor?
You'll always be told the scale factor.
Oh, you will?
So it says graph triangle ABC and its image after a dilation with a scale factor of 2. So let's graph our pre-image first. So we need little ABC. So negative, or no, not negative. 2, 1 is A. 4, 1 is B. 4, negative 1 is C. Okay. How do we now find our image point?
Multiply the number by 2.
Number by 2.
Yeah, you just type
Yes.
number by 2.
It's just like
So A prime is going to be what?
1 over 2.
4 comma 2.
So how did you get 1?
B prime is going to be what?
8, comma 2.
8 comma 2. What's C prime?
8 negative
8 negative 2.
Well, how's it negative 2?
Because it was a negative 1.
Josh, if you multiply a negative number by a positive number,
So graph these points and then we'll see what our image looks like.
Negative 1 is just 1.
So 4, 2.
we're not multiplying negative
But
by
we're
negative,
multiplying
we're
by
multiplying
2.
negative by a positive.
Oh, it's negative 2 then.
Thanks, Josh.
Yeah, it is.
Guys, isn't Josh just such a genius?
Bro, I actually am like a genius.
Uh-huh.
Alright, so as you can see, it got bigger by about double. Because it has scale factor of 2.
Whoa.
Wait, it's actually double.
Alright, on to the next page once you have that. So we can look at our similarities.
Similarity. Why is there so many rows?
Yeah, this is a lie.
One page, front and back.
That's it, bro.
You guys should not be overwhelmed by that.
Wait, this is the last one.
This is the last page.
We're also
No.
doing like 2 seconds. We're doing 0.5
I get overwhelmed.
Alright. So, what is a similarity?
It's like when it's the same.
Similar.
It's like saltine, but like.
When they're similar, yes. So it's a dilation is a transformation that preserves shape but not size. All of the other transformations we've done, the size and the shape has been preserved, right?
Yeah.
They just slid, rotated, moved, flipped, something. But they were always the same size and the same shape. Now, we have the same shape, but the size is changing. So, this is called a non-rigid motion. Remember when I mentioned that last class? I was like, have you heard of a rigid motion? This one is a non-rigid motion because it's not preserving our size. Okay. So, a similarity transformation is a dilation or a composition of rigid motions, translations, reflections, and rotations, with a dilation. So if you ever use a dilation in it, it is no longer a rigid motion. Similarity transformations preserve angle measures only. So it says when the scale factor of a dilation is 1 or negative 1, the side lengths don't change, and it really isn't a meaningful dilation at all. Okay. Two geometric figures are similar figures. What is this thing called, if and only if?
Biconditional statement.
Okay, look at that. You might be prepared for your midterm.
Let's go, Josh.
Two geometric figures are similar figures if and only if there is a similarity transformation that maps one of them onto the other. All right.
Oh, wait, when is our midterm?
The very last day of school, the 22nd.
Oh, you're
Oh, I
doing
thought
that
you
to
I
us?
thought you did that end on very last day of school.
It has to be. Your exams have to be the 21st or the 22nd.
Why can't it be the 21st?
Wait, what if I just miss those 2 days and then get
Then
it,
you take a
we get,
0.
Like, when
And you have to take it next semester when you come back.
Oh. I'm feeling sick already.
All right, so number 4 says graph triangle ABC and its image after the similarity transformation. So we're going to do a translation first and then a dilation after that. So graph your pre-image to start. So negative 4, 1,
1, 2.
negative 2, 2,
Oh, no.
Negative 2, 1. All right. My first image, because we're going to have 2. We're going to have a double prime. So what is A going to become?
1, 2.
Yeah.
Okay. I just want to make sure people know where that came from. What did he do to get to 1, 2? We added 5 to x, which gave us the 1. And then we added 1 to 1, which gave us 2. All right, what is B prime going to be? 3, 3, 3.
3, 5.
I have to like stop and stutter for a second to think if that's right. C prime is going to be at what?
Jeez, man, good stuff.
3, 2. All right, graph those points. So 1, 2, 3, 3.
A, B, C.
You guys cracks me up. You're just like, yeah.
Really not.
All right. Was this a rigid motion or no?
No.
Wait, what's a rigid motion?
Yeah, what is a rigid motion?
It does 2 things. So, like 2 different. 2.
Oh, no.
Oh, yes, yes.
Yeah, you know what I'm trying to yap about here. Like it does.
A rigid transformation preserves shape and size.
Oh,
yes.
Yes, it is a rigid
What did you grab?
This one was a rigid motion. Now let's do our second image. Now we're multiplying everything by 2. So what is A double prime going to be?
2, 2, 4.
Which point are you using? Your pre-image or your first image?
First.
Your first image. You're going to what you just used. So
Oh.
multiply both of these by 2, and what do we get?
2, 4.
2, 4. What is B double prime? 6, 6. What's C double prime?
6, 4.
This is 4.
All right, graph these 3 points, and then we'll see what we have.
5, 6.
2, 4.
You're 5'8", bro? My God, you said I'm fully grown. I should be 5'7", bro. I'm already taller than both of my parents, bro. By a lot, bro. I'm gonna stop growing any time now, bro.
Okay, was this a rigid motion?
No.
No.
Did we preserve shape and size?
No.
No,
Just shape.
just the shape. Okay, look at us cruising along. Number 5 says, describe a similarity transformation that maps the trapezoid PQRS to the trapezoid WXYZ. So it's important to know which point goes with what. So what point is the image for P?
P. Oh, W.
P became W. What is the image point for Q?
Star got it now.
X. The image point for R?
Y.
And S?
Z.
Okay, make sure that you're following that there. So, what we're looking to see is how did P, which is at negative 6, 3,
Times negative.
get to 2, 1?
Yeah. Time.
Plus.
Times 2 plus 2.
So, let's figure out what happened.
3.
PQ used to be how long?
Divided by negative 2.
Oh, times 2. My God.
3.
Okay, side conversations need to end so that people who want to learn can. PQ used to be 3.
3.
In the image, it's how long?
1.
So what would we do to get from 3 to 1?
Divided by 3.
Okay. And let's check if that works for everything else. So from PS to WZ, it was how long?
6.
6.
And it became how long?
2.
So what did we divide by?
2. Or 3.
3. Okay, let's keep checking. How long was SR?
5.
6.
Or 6.
1, 2, 3, 4, 5, 6. And it became how long?
2.
Okay. And then the diagonal, I don't really want to count that, so we're going to hope for the best there.
No, I can count it.
All right, so we did a dilation of how much?
It's 6.
Negative 3.
I need
Oh.
How do we write divide by 3 as a dilation number?
Just
Point
like this.
3.
1/3. Or 0.3 repeated. Is that the only thing we did?
No.
No.
We did transforming.
Then
we rotated.
we
reflected
300
it flipped.
or 180.
We reflected it. Okay.
We did reflect it. What did we reflect it over?
180.
Y-axis.
Oh, I don't.
So if we reflect over the y-axis, yes, it stays on the y-axis for r and y, so this would be a reflection over the y-axis.
This is actually kind of easy.
Good.
Yeah.
I think my teacher just got it once yesterday.
I think so. Yeah.
Because I started crying about 6 times.
All right.
Yeah. That.
The last thing we're talking about is those negative scale factors. So a negative scale factor is going to rotate something 180 degrees. It's flipping it the other way. When k is greater than 0, a dilation with a scale factor of negative k is the same as the composition of a dilation with a scale factor of k, followed by a rotation of 180 degrees.
Why would I do that?
So, you can do it either way. You can break it into 2, or you can do it at once. So it says, using the coordinate rules for a dilation and a rotation of 180, we can write the rule for a negative scale factor as this. So xy gets multiplied by the scale factor. So we got x, or kx and ky. We just multiplied by a scale factor. And the rule for rotating something 180 degrees was to just make both of them negative. So that's what we did here. So instead of having to break it down into 2 steps, you could if you wanted, you can just take xy, multiply them by k, and make them both negative. And that would take your pre-image of this little dude here to become this figure here after a scale factor of negative k. All right. How do we feel about this?
Feel
Hey,
good.
good.
Sure.